Welcome to Unit 2 of Computer Organization and Architecture. In this today's session, we are going to learn about one of the most important components inside the CPU registers. Students, whenever we talk about CPU performance, we usually discuss the ALU control unit, memory, cache, and so on. But there is another very important component that works very closely with the processor, that is register. Registers are very small, extremely fast storage locations present inside the CPU. In this session, we will understand what a register is, why registers are required, different types of registers, general purpose and special purpose registers, status flags, the program counter, and finally the register naming convention under x86 64 processors. So let us start with the basics. First, let us understand the basic question, what is a register? A register is a very small and very fast storage location located directly inside the CPU. Think about the CPU and as a worker who is performing a calculation. If the worker has to repeatedly go to the distant storage room to get every small piece of information, the work will take more time. Instead, the worker can keep the frequently required information on the table itself. Similarly, the CPU keeps frequently required data and intermediate results in registers. The slide shows that registers are located very close to the ALU and control unit. The ALU performs arithmetic and logic operations. Before the ALU performs an operation, the required operands are normally brought into registers. For example, suppose we want to calculate A plus B. The values A and B can be loaded into registers. The ALU takes these values, performs the addition, and the result can again be stored in the register. So, a register acts as very fast working storage for the CPU. Now, notice the comparison given in this slide. A typical register access can be less than 1 nanosecond, and the registers are significantly faster than main memory. However, registers are very small in size. Modern CPUs may have only a limited number of general purpose registers. So remember this simple relationship. Registers are extremely fast but very small. This is one of the most important points from this slide. Now let us understand where registers are positioned in the overall memory hierarchy. Students, this concept is very important in computer organization. As we move closer to the CPU, the storage becomes faster but generally smaller and more expensive. At the top, we have registers. The slide indicates approximately zero point 0.3 nanoseconds as the typical access time and less than 1 KB as the indicated storage size. Below registers, we have L1 and L2 cache. Cache is slower than register, but it provides much more storage. Next, we have main memory or RAM. RAM provides storage in the GB range, but its access time is much higher compared with the registers. Finally, we have disk or SSD storage. Storage device provide very large capacity, typically in the TB range, but they are much slower than registers. So students, remember the order: registers, cache, RAM, secondary storage. As we move from registers towards storage, speed decreases while capacity increases. A simple way to remember this is fastest and smallest at the top, slowest and largest at the bottom. This hierarchy is necessary because building the entire computer memory using the faster technology would be extremely expensive. Now let us classify registers. Broadly, the slide divides a register into two categories: general purpose registers or GPRS, special purpose register SPRs. First, let us look at general purpose registers. General purpose registers are flexible registers that can be used by programs and compilers to store data, addresses, and intermediate results. For example, during the arithmetic operations, registers can hold the operands and the intermediate result. They can also be used for temporary variables and other computational requirements. So the important word here is flexibility. Now let us come to special purpose registers. Special purpose registers have a specific function. They are not simply used as general storage locations. For example, the program counter or PC keep track of the next instruction to be executed. The stack pointer or SP manages the stack. The flag register records the status or outcome of operations. So students, the easiest way to remember the difference is GP or flexible use, SP or dedicated use. This distinction is very important when you answer questions about CPU registers in examination. Now we'll look at a practical example using x86 16-bit legacy register set. The slide shows 4 important general purpose registers: AX, BX, CX, DX. Let us understand their traditional roles. First, AX, accumulator register. AX is traditionally associated with a specific operation and certain input or output operations. Next, BX, base register. BX is commonly associated with folding a base address, especially in indexed memory access. CX, a counter register. As the name suggests, CX is typically used as a counter. For example, in loop operation, CX can be used to keep track of how many times the loop should execute. It is also associated with the shift and the rotate instructions. Finally, DX, data register. DX is used in several arithmetic operations, particularly multiplication and division, and also in certain IO operations. Students, one important point here is that these names come from the traditional x86 architecture. So don't assume that the modern processor restricts each register to only one purpose. The important idea is that these registers have traditional or special roles associated with a certain instruction. So remember, AX accumulator, BX base register, CX counter, DX data. This is a very common question area when studying x86 registers. Now let us move to special purpose registers. The slide introduces 5 important registers: PC, IR, MAR, MBR and SP. Let us take them one by one. First, PC, program counter. The program counter contains the memory address of the next instruction to be executed. This is extremely important. The PC tells the CPU where it should fetch the next instruction. Next, IR, instruction register. The instruction register holds the instruction that has been fetched and is currently being decoded and executed. Then we have MER, memory address register. MER contains address of the memory location that the CPU wants to access. For example, the CPU wants to read data from memory location 2000. The address 2000 can be placed in MER. Next, MBR, memory buffer register. It holds the data being transferred to the CPU and memory. I'll repeat, it holds the data being transferred between the CPU and memory. Finally, we have SP, stack pointer. The stack pointer points to the top of the stack and is important for function calls, returns, and stack operations. Students, please remember these 5: PC, next instruction address; IR, current instruction; MER, memory address; MBR, data being transferred; SP, top of stack. This simple association will help you answer many examination questions. Now let us look at the another important special purpose register, the status or flag register. Students, whenever the CPU performs an arithmetic or logical operation, we may want to know what happened as a result of that operation. For example, Was the result 0? Was there is a carry? Was the result negative? Did overflow occurs? The CPU records such information using flags. A flag is generally represented by a single bit. The slide shows several important flags. First is zero flag or reset. It indicates that the result of an operation was 0. Next is carry flag or C. It indicates an unassigned carry or overflow condition. Then we have a sign flag S. It indicates the sign of the result. In the context shown here, it indicates a negative result. Next is overflow flag O. Overflow is associated with the signed arithmetic exceeding the representable range. Then we have a parity flag P. It indicates the parity condition of the result with a slide specifying an even bit count. Finally, we have an interrupt flag I. It indicates whether interrupts are enabled in the processor context shown. Now, why are these flags important? Because conditional branch instructions can examine these flags. For example, suppose we perform a subtraction and the result is 0. The 0 flag can become set. A subsequent conditional jump can check the 0 flag and decide whether to continue with one sequence of instruction or another. So students, remember, the flag register tells the CPU about the outcome or status of operations. This is the connection between arithmetic operation and the conditional program execution. This diagram represents how different registers is connected to the CPU and with the arithmetic and the logic unit along with the data bus, address bus, control bus. Now we come to a very important concept, the working of the program counter or PC. Please pay close attention to this slide because it connects the register concept with the instruction cycle. The program counter contains the address of the next instruction to be fetched. The diagram shows the CPU on one side and the main memory on the other side. Let us understand the process step by step. The PC contains the address of the next instruction. That address is sent towards memory through the address bus. The instruction stored at that memory address is fetched. Once that instruction is fetched, it is placed in the appropriate CPU register and decoded by the control unit. The control unit determines what operation has to be performed. Step 3. Execute. The instruction is then executed. If it is an arithmetic or logical operation, the ALU may perform the operation. If it is a memory operation, appropriate data transfer takes place. Step 4. Update PC. After the instruction has been processed, the PC is updated so that it points to the next instruction. For sequential execution, the PC is normally advanced by the instruction length. For example, if an instruction occupies 4 bytes and the current PC is 1000, the next sequential instruction may be at 1004. But there is an important exception. If the current instruction is a branch or jump, the PC does not simply increase to the next sequential address. Instead, it is loaded with the target address. Similarly, during an interrupt, the PC can be loaded with the address of the appropriate interrupt service routine. During a procedure call, the control flow can move to the address of the called routine. So, students, the most important statement is the PC always identifies where the CPU should fetch the next instruction from. Without the program counter, the CPU would not know the correct sequence of instructions to execute. Let us now look at the x86 64 register naming convention. The slide introduces an interesting concept. One physical register can be accessed using different names depending on the width of data we want to access. For example, consider REX register. At 64-bit, it is called REX. The lower 32-bit view is called EX. The 16-bit view is called AX. The lower 8-bit view is called EAL. Similarly, we have RBX, EBX, BX, BL for different width. Then RCX, ECX, CX, CL and RDX, EDX, DX, DL. The slide show also shows RSP and RBP with their corresponding 32-bit and 64-bit names. Why is this useful? Because different instruction may operate on different data width. For example, sometimes we need to process a full 64-bit value. At another time, we may need only 32-bit or 64-bit or 8-bit portion. So the processor provides different names to the access different portions. Students, this is an important distinction. These names should not simply be understood as completely independent register. They represent different views of the register architecture. RAX, RAX 64-bit, EAX 32-bit, AX 16-bit, AL 8-bit. This naming convention is very important when you start learning assembly language programming. Now let us quickly summarize this session. First, registers are among the fastest storage locations available to the CPU. They are located inside the CPU and are used during instruction cycle. Second, we studied the difference between general purpose registers and special purpose registers. General purpose registers provide flexible storage for data, address and intermediate results. Special purpose registers perform dedicated functions. Third, we discussed the status of flag registers. Flags such as 0, carry and sign provide information about the outcomes of operations and can be used by conditional branch instructions. Fourth, we studied the program counter. The PC contains the address of the next instruction to be fetched. During normal sequential execution, it advances to the next instruction. During a branch, jump, interrupt or procedural call, it may be loaded with a different address. Finally, we looked at the x86 64 register naming convention. The registers such as RAX can be accessed at different width using RAX, EAX, AX and AL. So students, if you remember only few things from today's class, remember this. Registers mean very fast CPU storage, GPR mean flexible purpose register, SPR means dedicated purpose register, PC tells where the next instruction come from, IR holds the current instruction, MAR holds the memory address, MBR holds data transferred to or from memory, flag records status of the operation. And finally, RAX, EAX, AX and AL represent different width views in the x86 64 register naming convention. That brings us to the today session on CPU registers. Thank you for watching. In the next session, we can continue with the next important concept of computer organization and architecture. Until then, keep learning and keep practicing.